halt erstmal pingen und dann
ich werde nicht pingen und dann weil ich keine Internet also jetzt lang auf 192 ja. Cool, immerhin.
deswegen zwei Kanäle.
so, natürlich, wenn das weißt, wenn ich diese kannst du uns so ein Internet Io
Can everybody hear me? Or it's fine? Okay. So if everyone sits down, I guess we can start. As you see, my name is Peter. I'm from Belgium. I do mainly embedded systems development, which explains a bit why I'm involved in this JTAG team. And I will give a presentation on how we hacked actually we took a commercially available device, a simple wireless access point, and we were working on trying to get it to run Linux, and we use it in a kind of a mesh, in a wireless mesh. You could ask why would you hack existing devices? Why would you not just use them as they come, or make your own device if you want to do something special? Well, there are many devices which, hardware-wise, are quite interesting because they are low power, they have some nice interfaces like Ethernet or wireless LAN or serial ports or other video outputs. They are typically cheaper. In some cases, it's cheaper to reuse existing commercial hardware because it's certainly if the interfaces and the amount of CPU power fit your intended purpose. This is certainly true for stuff with regard to wireless, and it's yeah. One of the reasons is obviously that because they are mass produced, it's far cheaper to use an existing design than to try to do your own thing. And the other reason is that some of the components which are typically used in modern devices, like PGA chips and stuff like that, are quite hard to get solved yourself. So it's very tricky to avoid design at the level of the commercial products. It's always obviously interesting to do. It's also fun and challenging to reuse existing hardware for purposes it was never meant to be used for. At least I like it. It seems that quite a number of people like to do such things. So that's another reason, just for fun, and because it's possible, it should be done. I'll give a quick overview on what the system on a chip is. The rest of the presentation will go first. I will give a quick overview on system on chip design. I will then go in a bit more detail on what JTAG exactly is, where it comes from, what you can use it for. Then I will describe what kind of free tools there are available to use JTAG, and then I will give an overview on what we did with JTAG, how we used it, and how far we got with our intended project. So system on a chip is typically what people use for building commercial scale cheap boxes like access points or wireless routers or these bridge devices, they call it DSL wireless routers and this kind of stuff. They typically contain some kind of CPU core. Depending on the application, it's either very cheap core, 8 or 16 bits, or more a 32-bit real CPU, which in some cases has memory management. Typically, CPU architectures you're likely to encounter on the ARM, MIPS, and PowerPC. You obviously have some memory controllers to be able to access SDRAM, flash, static RAM, whatever. Some timers for protocol handling and context switches. Obviously, interrupt controllers. There are always GPIO lines, just general purpose I/O lines which you can use as input and output. They're connected to LEDs or buttons or all kinds of simple things. Sometimes you have these simple serial interfaces. There are typically two wire interfaces which have a data and a clock line. Very common examples are I2C, which was designed by Philips and which is used to drive small E2 prompts to store settings or the MAC address or something. Or SPI, which is from Motorola, which has a similar purpose. Standard serial ports are sometimes available. Ethernet is becoming more and more standard. Lots of the modern system on chip designs have at least one Ethernet, some even have two. And then there is typically some kind of an external bus interface, depending on how high-end your chip is. It's sometimes a simple static memory controller line interface. That can also be a full-fledged PCI bus, which is used for extension peripherals and stuff. What is JTAG? JTAG is actually a abbreviation which stands for Joint Test Action Group. It was a kind of a specification committee and group within IEEE. They produced what's called the IEEE 1149.1, the boundary scan specification. The basic idea is that they have a big shift register which goes around your whole chip, which allows you to drive every single. So you can read or set or reset every pin on the physical chip. That was the original idea. And the reason they wanted to do is to facilitate board level tests. So you imagine you make a whole PCB with lots of complicated chips. You produce these boards, and then you have to make sure that they work. So it's not like you can measure every connection on the board. That's far too difficult and far too time consuming. So they devised this boundary scan with a simple serial interface. I will describe this later, about 4 and the other the same later 5 serials these days. They can access all the complicated chips, drive the pins, set a pattern on it, and then all the chips read out the pattern and see if all the connections are okay. As I said, it's a serial input. It has, it's also designed to be daisy chained. So normally there are you need 4 to 5 external pins, and that's it. And then you can daisy chain all the chips which you want to access via JTAG one after another. These signals are the TDI, which stands for test data input. So that's obviously it's also always looked at from the point of the chip. So the test data input is actually on the controller side of the device, which actually uses the JTAG will be the output. The test data output is obviously the other way. So if you daisy chain them, you can just daisy chain the TDI from one chip to the TDO from the previous one. Obviously, you also need some kind of clock to indicate when the data lines are actually valid. That's all using TCK. As you will see, I also will explain later, there is a whole state machine involved. This TMS signal is used to control as an extra input into the state machine. Then there is TRST, which is for test reset. It's actually to reset this internal controller state. Not all chips have this. In some cases, you just have to shift a bunch of pulses on the TDO line, and then normally the whole state machine is set up that it always ends up in a well-defined state. But in more recent designs, they added this TRST, and you sometimes have to set a pulse on it, otherwise the chip doesn't even react on any JTAGs. So it's all daisy chain, and it's based on this scan chain concept. Like I said, it's a large shift register which goes around the whole chip and allows you to control all the pins, or data pins, whatever you want to do. Each of the chips which supports JTAG has what they call a tap controller. It's a test access point controller. In principle, you could have multiple tap controllers in one chip. I have seen this on one occasion, but most of the time you have only one tap controller on the chip. There are mechanisms which you can use to auto-detect JTAG chips, so you can find out how many tap controllers are there, and typically also how many chips are on the chain. The tap controller is controlled by a standardized state machine that I'll show you on the next slide and give you some explanations about it. It has normally 3 registers, although the last register is optional. The boundary scan register is actually the register which describes this external scan chain that I explained before, which controls the pins. Bypass mode is actually a 1-bit register which just connects the input to the output. So it allows for the daisy chain which you can put all except one of the chips in bypass, and then they will just pass on the data, and only one which is not in bypass mode will then actually do something with the bit stream, with the commands coming via the serial inputs. There are a few instructions. There are 3 mandatory instructions, being bypass, which puts the controller in bypass mode. Xtest, which actually connects the inputs to the output, to the boundaries, the input and the output to the boundary scan register, so that the boundary scan register you can actually drive and read the signals back. Sample and preload allows you to load the scan registers without actually affecting the outside world pins. So you can set up a pattern on the outside world on pins, and then go in X test mode and read it back. This can be useful to first set some pins, then trigger some other things to happen, and then read all the state of the input pins back. There are some extra instructions which are not mandated by the standard, which are quite common. One is the ID code, which allows you to access the ID codes register. With the ID codes register, as you could guess, identifies the chip. So by this you can actually see which chips are on the chip. Not everyone implements this. Not everyone implements it correctly. So the value of the ID code is not that high as you would expect. Then there is the in-test instruction, which is it's similar to X-test, but there are some subtle differences, which are probably would lead us too far to try to explain those. This is the magic state diagram. As you can see, I hope everyone can read this because I'm not sure if it's large enough. No, I don't think this thing has a zoom feature, so it's not annoying. But basically, the basic thing you have to get this, you have this TMS signal, which I explained before. Sometimes governs what you exactly do. So if you see you will see that there is a big branch in the beginning of the state diagram. That's the one which selects if you will be writing to the instruction register. So if you'll be giving a new instruction to the tab controller, or if you're writing to the data register. So, for example, if you would want to read the ID codes register, you first select. You first manage to get into the select instruction register scan. Then you shift in the instruction register, the ID codes instruction. Then you get back to reset run test idle. Then you can shift out the data register, which will contain the chip ID. The instructions, the actual bit patterns of the instructions, and it's certainly the chain, the signals which are described by the JTAG chip are obviously not standardized in the sense that, every chip is different, so you need a different number of signals, which ones are input and output, and drive state are obviously chip dependent. To be able to make uniform test tools, which can handle any chip, they invented the boundary scan description language, which is a description language which describes what the JTAG chain actually does. It actually describes three different things. First, which signals are in the JTAG chain by name. So, like for example, A0 for the address bus signals, or the data bus signals on the GPIO lines or whatever. If they are input and output or tri-state signals. The instructions accepted, that's obviously those three mandatory instructions, but any manufacturer can add its own instructions, which are accepted by the tab control, and can describe them in the BSDL. As I said, the actual bit patterns for even the standardized instructions are not fixed, so the BSDL file also has to describe which bit pattern you have to send to be able to do the X-test command or this handle command. The length of the registers is also chip dependent, so that's also a parameter which needs to be described in the BSDL. Also, if there are more registers than the standard ones, that obviously needs to be described as well. So up to now, I always talked about how to control external pins and external stuff. That's what I call external scan chains. The concept of internal scan chains is something which is not really standard, but I think it helps to clarify what you can do. In the external scan chain, all the pins are actual physical device pins. So if you set something on it, you can probe with a scope or looking into it and see it moves. External scanning, as I said, allows direct access to any pin. It does not rely on any of the internal components. So for example, you can access directly the data and the address pins of the device, even if the CPU core doesn't work, or even if the memory controller is not programmed. That's very important, because it allows you to read and write, for example, the flash memory, even if the flash memory is completely empty or contains completely invalid contents, and if you would boot the device, misprograms the whole chip so that the whole thing locks up. But because you don't use any of the actual internal logic of the chip, you can still erase your flash and put in a valid image. If you are playing with devices, this can become very important. Otherwise, you quickly have a dead port which becomes useless. You can, as I said, it's used for connection tests during manufacturing, but that's not something I'm not very much interested in. But you can use it to read and write a flash, even if the CPU core doesn't let you do that. Then there are internal scansions. This is a concept which was added later, because people realized that there would be, we now have this simple serial interface to our CPU or whatever. Perhaps we can do much more than only use it for test purposes. We could, for example, use it for debugging. Most of the modern CPU cores have an ICE-like debugging feature. What I mean is that it's hardware assisted in the sense that, in principle, the software cannot manage to bring the CPU in such a state that the debugger doesn't work anymore. In practice, it's a little more complicated than that, unfortunately. For those who know, the concept ICE comes from the 8-bit world, where people had actual big boxes which emulated a complete process. So they used special chips which rolled out normally internal signals to the outside world, so they could actually do hardware step by step. Some mainly ARM also uses this for what they call a debug communication channel. We'll detail this later. And if you have programmable logic devices like FPGAs or CPLDs, they can also be programmed via JTAG. Most of them also have another programming method, which is typically used in the field when the device is actually programmed by its own CPU or something like that, but they can also be tuned by FPGA. Obviously, because these internal scansions were never standardized, that requires some extra tab controller commands, depending on, and those are more or less proprietary to the specific implementation. So debugging via JTAG. The idea is that you can control the CPU core completely using the JTAG interface. Obviously, how this exactly works is dependent on the CPU core, because you typically have to use special debugging hardware. Most of those processors, almost all of them, have special breakpoint registers, which sometimes can be accessed from within the CPU, sometimes they can't. Those breakpoint registers allow you to actually stop the processor under, certainly when it tries to execute a specific an instruction of a specific element, but in some cases you can also use it to stop the processor when it tries to access a specific memory location, even depending on if it's an internal write. JTAG debugging also allows you to insert instructions in the CPU pipeline. So you can actually add a JTAG, walk in a new instruction, and have the CPU execute this. You would wonder why do you need this? I mean, there is already code. Well, one of the reasons you need this is that obviously if you write a debug, you want to know the contents of the registers, or you want to be able to write to the register. And almost all CPU implementations solve this by allowing you to do a load or store, and then so you can shift in a load or store instruction, and then by shifting out the data lines of the scan chain, you can actually read what load or store did, or you can, in case of a load, you can first put in the value you want to load. In case of a store, you can execute the store and then read the registers out. So that's the way they implement reading and writing registers, and you can also access memory via this way. But be aware, if you access memory by controlling the CPU core via JTAG, you're not directly controlling the output pins. You're actually writing code which gets executed and accesses memory. This means if your memory controller doesn't work, if you have a virtual memory system or whatever, it might not work. It might hang. For example, if you would access a memory location and trigger a bus cycle which never ends, you might just hang the core. In some cases, unfortunately, specifications on how this exactly works are only available on non-disclosure. This is typically the case for PowerPC, it seems. Yeah, at least for ARM, Xscale, and MIPS, I found some detailed specifications on the web, so it should be okay. If you try to debug the Linux kernel, or more in general, any kernel which uses virtual memory, there are some. You have to be aware of the fact that it interacts with memory management. But you can certainly not always. You cannot use JTAG debugging for debugging userland stuff, because the JTAG interface and the debugger behind it doesn't know anything about the current memory state. And as you will remember, every process in the Unix system has its own memory space. In every context which you change the page tables, which means as that you can also actually interact directly with the user. A few examples of how common CPUs implement this concept. One of the popular chips is the ARM 7, 9, 10, 11, I don't know where they are. They all use a similar concept. What they call the icebreaker microsat. It's an extra component which they integrate on the chip. It offers two hardware breakpoints which are only accessible by JTAG. So you can't access them from the CPU. Each of those hardware breakpoints actually matches another's data and a control value. So you can mask the others, see if it matches, and then match it with the value. It will trigger the breakpoint. Same for data. And the control bits are stuff like if it's a read or write access, if it's a color or data fetch, if it's a 8 or 16-bit or 32-bit access, if it's a user and or supervisor mode access, things like that. And I think there is also one external scheme, so you could in principle only trigger the breakpoint if some external condition happens. This allows you, for example, to do with two hardware breakpoints. You can easily, the common trick they do when it's two breakpoints, that's not enough. When I'm programming, I want, or debugging, I typically want one or two breakpoints. What they do is for common cases, when you debug code which is in memory, they write a magic value, magic instruction, which is normally invalid at that location, and then they say, okay, if it's instruction fetch, and the fetch returns this magic value, then it's a breakpoint, independent of the address. So, and then they just write everywhere where they want this magic pattern, and when the CPU encounters this, it will stop, and then the debugger will be notified when something happens. It then obviously has to rewrite the real instruction, go one step further and do the whole operation again. Those hardware breakpoints can also be used in a chained mode. So you can say, only start looking for the condition programmed in hardware breakpoint 1 and hardware breakpoint 0 has been taken. They also implement a debug communication channel. From the CPU side, this looks like a kind of separate processor. You have two registers for reading and writing, and you can see if the JTAG debugger already gets your value and vice versa. This is quite useful because it allows you to have a simple output channel without any external hardware, without having a functioning UART, without having anything really working from the external logic. You can still send messages from your program running on the CPU to the outside world. In principle, you can also do input, but the problem is that this DCC does not have internet, so you should call for your input, but it can. As memory accesses are always done by the CPU, you cannot actually. They are translated as normal memory accesses from any code which runs. So it's not like you can, if you have a broken MMU table, there is no way to go via JTAG and look in, at least not via JTAG, even via the speakers, so there's no way to actually access the physical memory and see what's running in the page. And it obviously relies on correct configuration of the memory controller hangs, then yeah, you're lost. Another implementation example is the Xscale. That's a bit different. The Xscale is Intel's implementation, Intel's successor to the StrongArm, and is used in quite some of the modern PDAs, but also in all kinds of portable and networking applications. The Xscale has debugging registers, which are part of the normal coprocessor register set, and they can be accessed like they can be accessed from normal code as well. They are not special to the JTAG debugging. What they do, their trick is they have a 2 kilobyte cache, which you can program to hit on specific memory locations, and which can only be written to via JTAG. So you can only load something in this cache via JTAG. The CPU can obviously read it, but normal code can never write to this code. They have a special trick. They have a kind of a special mode where they can, because these debugging registers, when they trigger a breakpoint, they would normally trigger some kind of an exception. But with this special interrupt trick, they can manage to redirect the exceptions to their own code. So if you want to write a debug using this method, you have to write a 2 kilobyte assembly program which fits in this cache. And obviously, this assembly program somehow has to communicate with the host debugger to set a breakpoint to read memory. And this has to go via JTAG. So they have a kind of a special debug communication channel they implement. They implement it as special JTAG instructions which allow a cache code and a host debugger to send messages to one. On the other hand, it's more or less the same as the ARM strategy. They have memory accesses that are just like any memory access which is executed by the processor. And obviously, it needs a working memory controller. Now, the question is, how could you interface to JTAG? It's all nice that we have this, but now I want to control the JTAG device from my PC. How to do this? The very cheap way is what is typically called in parallel port dongle. It's very simple. It's actually a one-chip. It's a one-chip device, which is just a brief release. The only reason this buffer is is that the voltages on the parallel port are normal 0 to 5 volts, while most of the target CPUs are 3.3 or sometimes even 2.8 volts, I think. So you need some kind of buffering there. This buffer is powered by the target, so the inputs can tolerate the 5 volts, but it will never output something which is higher than the input voltage of the chip. So you could just connect all the JTAG scenes to parallel port or input the correct lines, and the rest you do in software. There are lots of implementations, some are commercial, and a lot of them are free. There are some which lack this necessary TRST signal. Mainly these, if you have ever done FPGA or CPLD stuff with Xilinx or Altera, you probably remember the Xilinx parallel cable or the Altera byte blast. These are all implementations of this parallel port dongle thing. But the CPLDs or FPGAs never use the TRST. So you cannot really use those devices for debugging processors, at least not all of them. The big disadvantage of this strategy is that it's slow. If you think in terms of bandwidth, I think you can perhaps get a few hundred kilobits. But you have to remember that this whole JTAG protocol has quite some overhead because you have to walk through the state machine and stuff like that. So if you use this for writing to flash, you will get a few kilobytes per second, which is, if you have to write a 1 megabyte flash, it takes a while. And there are JTAG interfaces which use extra hardware. They interface to a parallel port or USB these days, and some of the more expensive ones even have Ethernet. They typically use programmable logic to at least do the low-level protocol, the shifting of the bits and stuff like that. And some have, certainly the ones with Ethernet, also have a CPU to handle the TCP/IP stack. Unfortunately, I have never seen a free implementation of this idea, only commercial ones, and they are not cheap. And the other big disadvantage, because they are proprietary, is that they are not as flexible as the parallel port. Because with this simple dongle, you can control, you can flash a board which has a big scale, or a strong arm, or a normal arm, or a MIPS processor, or whatever. As long as you have the BSDL files and you know which signals do what, you can all access them. Now, the proprietary implementations are typically locked to one or a few chips, and if you're sometimes you have to buy a new box if you want to debug on the CPU, and sometimes they don't allow you to. Sometimes you can buy new firmware for them, but there is no, we don't have full control yet. The big advantage is that they are much faster. They can run JTAG up to 16 megahertz, and I think some even faster. If you want to go much farther than that, you would have to worry about cabling and reflection and stuff like that. Anyway. Software part, the main tool we used for this project, at least the open source tool we used, is the OpenJTAG team. It's actually part of the OpenWinCE project. It's a project which wants to do all kinds of open source stuff for Windows CE, but they also made this JTAG tool. It only allows you accessing external JTAG chains. It was never, at least up to now, it was never meant to access the internal chains or do JTAG debug. But it supports a lot of the common CPUs, and the list is growing every day. Regularly, you see people on the mailing list adding new patches for their chip they want to use on this tool. It also supports all common flash chips from Intel, AMD, SSD, and whatever. So it's quite likely that if you have a board with a common CPU and flash, that you can just use this tool and read out the flash. And certainly, for reading, it always works. That's the problem. If you want to erase it and reprogram it, you need to know which commands to send to the flash chip. But they have most of this too. It's also written in a quite extensible way. You can quite easily add your own CPU type if you want to, add a new flash chip if necessary. Because all the JTAG specific logic is in the library, and then you have per CPU, you have a file which knows how to do memory cycle. And that one actually uses them. They have their own file format for the scan chain description. I have no idea why they actually did this, but I think this is because the BSDL files are not always free, and they want to allow you to give you a way of making your own scan chain description without using the complicated BSDL stuff, which most of the time includes a bunch of things you don't really need in this case. But they have a converter which is a bit on the experimental side. It sometimes questions and it doesn't handle all BSDL files correctly. But using the converter and some experimenting, you can quite easily get a scan chain description for a new processor. Apart from the scan chain description, which tells you which signals are where in the scan chain, obviously you also have to know how to do a memory cycle. And that's typically done using a small CPU-specific C file, which has 4 or 5 functions for reading and writing. It supports a lot of the JTAG domains. I think almost all of them, which I ever saw, are supported by this tool. It's also geared towards using this parallel port domain technique. So even if adding a new JTAG domain is actually very simple, you just have to implement a few functions which tell how to read TDI, how to set TDO, how to set TMS and stuff like that. Another tool which I recently discovered, I didn't use it yet, is the JD debugger. It's a JTAG debugger for its skill, which uses the mechanism I described before. It has only been used on the PXA 250, and I think recently also on 255. It offers the remote GDB interface, so you start this program, and then you can just do a target remote localhost port name, and then you can start debugging your target remote. It's great for the McGregor Wiggle DOM, which is one of the commercial ones, but it has been cloned numerous times, so it's a quite popular DOM. But if necessary, it should not be hard to adapt this to other ones. The JTAG, and there is the JTAG tool. It's a program which is called JTAG. It was originally made by Digital, I think, although the history is a bit fake, so I'm not really sure. For programming, there's strong-arm evaluation modes. But then Intel took over the strong-arm, so they made a version of the strong-arm 1110. The Love project made a version for their board. But you can actually do only one technique, is reading and writing to Flash. It's faster than OpenJTAG, I think, because they use some shortcuts. I didn't really analyze in detail why the OpenJTAG is 20 to 30% slower than the JTAG tool, because they basically use the same technique, so they should be almost as fast. But the code is a complete mess, so it's not very helpful to hack on these things. So, yeah, it's perhaps useful as a reference, but it's not. Okay, so assume that you know which processor you have and stuff like that, and you have all the hardware. Then obviously, if you have an unknown board, how to discover where all those JTAG signals are on the board? Where do I have to solder my wires or plug in my cables to get this thing to work? As always, ask Google first. You might have been lucky and there might have been someone before you who thought of the same idea, who had more equipment than you. Or more luck. Some CPU vendors have standards for their JTAG connectors. For example, ARM has an older 14 pins and a new 20 pins connector. And certainly in first generation hardware, designers typically just slap on the standard connector because they also have to debug the thing, and they obviously want to use standard tools and not have to mess with extra wires, conversion, PCBs or whatever. They just want to be able to buy a tool, plug it in, debug. So certainly in the first revision of the hardware, it's not unlikely that the connectors or the pads at least for the connectors are still there. MIPS has a similar standard for their JTAG, extended JTAG thing. If that doesn't really work, you can always try to get the data sheet from the chip and the processor, and then trace the PCB, follow the PCB traces and use a multimeter to find out where they could be. That can be a lot of work and is not always very easy. If you have PGA package chips, then yeah, you're basically out of luck using these techniques because there is no way to even probe into some of these balls in the middle of the chips. But I have heard of people who actually managed to desolder the PXA from their iPads to find out where the JTAG thing was there. And it worked. So I have no idea if the iPad, if they managed to get that specific iPad to work again, they managed to find out where the JTAG things were. So they can start debugging actually. Frequently, you only have the pads or the holes in the PCB, so in a lot of cases, you still have to at least solder some wires or connectors to the board. I haven't seen a commercial product which was shipped including JTAG connector. That would be overly achieved. So, what did we do on our wireless access point? Wireless access point we worked on is the D-Link, the wireless X14 Plus. Actually, it's Division A because Division B is completely different hardware. It's also ARM, it also has JTAG, but it's a different CPU core, different chip. It's based on a Samsung controller, which has an ARM 17 50 megahertz. Has two stereo ports. Those question marks shouldn't be there, but okay. Has a network, GPIO, and has a kind of a PCMCIA-like external bus interface, which they use for the wireless card. And luckily, the datasheet could be downloaded from Samsung. The datasheet is not very clear, so badly written and impractical to use, but better than. And even more lucky for us because we want to have Linux on it and then be able to run the wireless mesh routing daemons on top of that. Someone had already done microcontroller export and even a kind of upload. So at least for the same chip, not for the specific board. The board has only 1 megabyte of flash, not too much, but it should be possible to get something out of it. It has 8 links on the and they use the standard JTAG, so it doesn't matter. Adding, soldering a few pins and off you go. For the wireless, they use this annoying TI chip, which is not yet documented. Please don't publicly documented. There's an open source driver for this, but as you will see later, there are some limitations on that. So what did we do? We obviously added the connector. The first thing we did was we read out the complete flash contents. We want to make a backup of what's there, so that if we manage to screw up, or if we want to be able to read registers from the controller when it runs its original firmware, we can still restore the original firmware. We also quickly analyzed the controls, and we saw that it's actually 3 parts. We have a small booter, which initializes the memory controllers, then uncompresses the firmware image, which sits behind it, which turned out to be a standard ARG file. So once we realized that, we could just copy that part of the complete flash contents, run an ARG element, we have uncompressed firmware, after encompassing the obviously anyway it fails, they give you some blinking LEDs to say that it didn't work. There's a third part in the image, which is the configuration settings. Okay. The next thing we did was compare the firmware images with the online firmware, so we made sure that that was okay. We erased this thing, we blurred it, that was awesome. And then we adapted there was a standard, what they call BIOS, but it's a bootloader thing. The only thing we had to do was adapt it for a specific flash, because this BIOS also wants to write settings to flash and didn't support a specific flash. We also added a small hack because we didn't have a serial port. We hacked the kernel to output the messages on the ARM debug communication channel. Basically, it runs Linux fine. The network works. You can download it. Doesn't cost anything. There are some things which are still lacking even more. First, the BIOS should be able to download an image file at FTP. That works, and be able to flash it. But obviously, unfortunately, it doesn't work. The driver for the wireless card was not yet completed because it was designed for hardware that normally use bus port, but this port uses the chip in a different configuration, and that's not yet supported. And then there is this Ethernet switch. The device claims to have an external Ethernet port and 4 internal ports in the switch. They actually use one switch chip. One port is connected to the Samsung controller, the other 5 ports are external ports, and they somehow manage to use VLAN-like things, I'm not sure how it exactly works, so that not all ports the traffic is not forwarded between all ports equally, so there is some kind of table rather than but unfortunately there is no data sheet on this piece, so you might never get this thing to work. On what we can do in the future with this JTAG thing. One of the things I've always been thinking of is that adding JTAG support or making a generic debugger for JTAG. For Xscale, we could integrate OpenJTAG with JTAG project perhaps. For ARM, I've never seen an open source free software debugger in ARM for JTAG. But the specifications are there, so in principle it can be done. A few people tried, but it seems that no one ever managed to get successful. MIPS, I never saw something on MIPS, although the specifications are there. RPC will be probably hard because all info I know is that you can't get to that. It would perhaps be possible to revert it because it's also based on the social stuff in the background. And the other way would be developing faster hardware. I mean, some of if you look at the commercial JTAG interfaces are nothing more than a CPU and a processor in some cases. And the rest is all software. So if you manage to get OpenJTAG, lead to a better free hardware implementation and a debugger that would have exactly the same result. So that would be another project to design into some links for people who are interested. First two are on the Samsung project, the others are on the OpenJTAG 2 BLE project, one of the hacktivism things from that. And the last one is one of the many clones of the common readers. Some of them we found on the web were broken, so we made a new one, and that's what we use as a reference, so we know that it works. Okay, that's it. If someone has questions, please feel. I don't know how much time we still have. Maybe 10 minutes or so. So, if you want to ask something, feel free. Yeah.
You probably have a cross compiler for
yes, I Yes.
So why don't you, is there no way to have a GNU debugger with a connecting to the target via JTAG?
Yeah, that's possible, but obviously you need some program which translates the GNU debugger commands to something which the JTAG core understands. And for Xscale, this is what the JTAG project does. It talks to GDB protocol on one hand and downloads this magic code in the Xscale and talks to that and makes sure that debugging actually happens. And for the other processors, this part doesn't exist in open source.
Okay, so for the Xscale it's possible to have it directly?
Yeah, it has only been tested on the PXAs. It should in principle also work on the other ones, but no one ever tried, so you might get some problems there. How fast you can clock the JTAG bus?
Yeah.
That depends on the number of factors. It depends on the wiring and how long you make your wires. It also depends on the chip, although many chips don't really specify this. But I think an upper reasonable limit would be 16 megahertz or so. Perhaps on some chips you can go faster, but I'm not sure. 10 megahertz is the standard, yeah. But I've seen chips which can do faster than that. And I also seen chips which don't handle 10 megahertz, so it's not really. Over there is someone who wants to ask a question.
If you have still unknown hardware,
Yes.
you only know this is my famous JTAG interface, how would you step into such a system? You go to the first point where the JTAG answers, and then what do you do?
Well, you first need to find out which chip it is, but you could, for example, try to read ID code registers and find out. And then, well, if you have some idea of which chip it is, and if you have a data sheet, you could try to find out the external scan chain, because all these, the controllers which have multiple scan chains, by default at reset time select the external one, because that's probably because they won't be compatible with existing test equipment. So and most of the time, the scan chain is actually just all signal pins, and forget about ground and VCC and things like that, in the order of the data sheet. So you just, if you can't start on one, pin one is typically the first one in the chain and stuff like that. So by that you can, even if you don't have the BSDL, you can typically you have a good chance of finding out what the pins do. If you then would manage to read out the flash, you can perhaps find out which CPU type you have by inspecting the disassembled code. That's not too difficult. It also helps if it's a commercial end-user device, and if you can get all the firmware upgrades, you can obviously try to find out the CPU type from the firmware upgrade. That's depending on how hard they made it, if that's possible. That might be a lot of work as well. Then if you are that far, then you could perhaps try to get your own code running if you know which CPU it is, and you have it compiled in the tool chain from it. It should be possible to get further. Okay, I think you've decided.
No, you don't have to do it automatically done. Yeah, every time you have to. was war eigentlich nächste Weihnachten wieder?
Was, wo man verpasst, oder?
Von der jüngeren Förder, die Exkursion in der Samstagsplatz oder was?
Ich kann es so nicht genau sagen, aber ich glaube, ich kann die Mine sagen.
Ja,
Kannst du mal...
die Folien von den Frostigen
Ja, das liegt am Referent. Da schießt vielleicht ein anderer Bockwasch.
weil ich noch zum Podcast jetzt mal wieder nicht gehört.
Willst du aktuell sehen, oder was?
Nee, die sind jetzt nicht gut, sondern irgendwelche Links drin.
Was ihr da aufnehmen, kommt das einfach irgendwie aufs Netz oder ist das Livestream?
Ich habe keinen Plan. Auf jeden Fall streamt es mal. Das Livestreaming auch.
Ja, hier intern oder auch?
Intern Livestream macht wohl wenig Sinn, oder? Soll ich mich da außen hin um die übers WLAN die Teile rein?
Aber ich habe nirgendwo ein Announcement gesehen von dem Stream. Also in der 1.2 schon.
Was man eingelesen hat. Rein, hat es ein Format auf meinem Kopf liegen und dann ist es Format aus. Geht rein, speichert bei uns auf File, dann habe ich einfach mehr Format gerechnet quasi. Dann lädt es das Format aus.
Aber das ist die Dezimalziffer?
Okay, Sven, dann irgendwann das ganze Dings eingefasst und dann im App-Format wieder auslösen. Tag, ich mache hier mit so. Was willst du machen?
Video
Mir ist wurscht, mal Video oder Audio oder. Ach so, oh, ich dachte, weil du hier rumhängst.
Ja, ich war vorher.
Vorher war ich noch alleine in der Planung, vielleicht bin ich auch weiterhin allein.
Aha, ach, das wusste ich jetzt nicht, ob da jetzt jemand.
Vorher war ich zumindest noch allein. Keine Ahnung. Ja, wenn du nichts zu tun hast, Ecos, ein Open Source Embedded Operation System. Ah, machst du jetzt hier mit oder was? Du stellst hier Video hin, oder? Okay, ich dachte, ich glaube, ich bin allein jetzt. War ich zumindest noch vor einer Stunde in der Planung. Ach so. Ja, das könnte ich glaube nicht. Aber ich bin ja ganz allein. Oder? Der also, gehst du jetzt oder bleibst du? Oder sollst du fort? Wenn du bleibst, dann gehe ich. Ja, zu den Ehren herrscht, dann ja, zu bleiben. Ich mache ein Video oder Audio? Dann nehme ich hier ab und mache gar nichts. Ein Video.
Volker kommt nicht. Der geht jetzt da rüber, glaube ich. Wir versuchen heute Morgen, wenn aktuell. Warum?
Also nochmal laut, hier ist jetzt der Zettel am Bildschirm, psychologische Aspekte von Computersicherheit. Wir haben einen Vortrag getauscht, weil die Bühne ist da logischerweise schlecht. Also einfach mal ein Wechsel spielen.